Imagine a world without portable power. No smartphones, no electric cars, no wireless headphones. It sounds impossible, right? Batteries are the unsung heroes of our modern lives, silently powering countless devices. But what exactly is inside these tiny powerhouses, and how do they work their magic? At its core, a battery is a chemical reaction in a box. Every battery, from the smallest button cell to the largest car battery, contains three fundamental components. You have two electrodes, a positive one called the cathode, and a negative one called the anode. These are separated by an electrolyte. The electrolyte is a chemical medium that allows ions to move between the electrodes. Think of it as a chemical bridge. This simple setup is what enables the flow of electricity. It's a carefully engineered system designed to facilitate a controlled chemical reaction. When you connect a battery to a device, a chemical reaction begins. Electrons are released from the anode, which is the negative terminal. These electrons then travel through the external circuit, powering your device. They then arrive at the cathode, the positive terminal. Simultaneously, ions move through the electrolyte inside the battery to balance the charge. This continuous movement of electrons and ions creates an electric current. It's a delicate dance of chemistry and physics, converting stored chemical energy into usable electrical energy. This process continues until the chemical reactants are depleted. Early batteries were often bulky and inefficient. Increasing battery power meant finding materials that could store more energy per unit of mass or volume. Scientists began exploring different chemical compositions and structural designs. The goal was to maximize the surface area for reactions and improve ion flow. This led to innovations like using different metals for electrodes and optimizing electrolyte formulas. Think of it like upgrading an engine. You need better fuel and more efficient parts. Each improvement brought us closer to the compact, powerful batteries we rely on today. The quest for more powerful and lighter batteries led researchers to lithium. Lithium is the lightest metal and has an incredible ability to store energy. In the 1970s, M. Stanley Whittingham at Exxon developed the first rechargeable lithium battery. It used titanium disulfide as the cathode and lithium metal as the anode. This was a groundbreaking discovery, but it had a significant drawback. The lithium metal anode was highly reactive and prone to forming dendrites. These tiny needle-like structures could short-circuit the battery, making it unsafe. Those tiny needles are called dendrites. They are crystalline structures that grow on the anode during repeated charging and discharging cycles. Imagine tiny, sharp spikes forming inside your battery. These dendrites can pierce through the separator, which is the thin barrier between the anode and cathode. When a dendrite punctures the separator, it creates a direct electrical path between the two electrodes. This causes a short circuit, leading to rapid heating and potential thermal runaway. This is a major safety concern and was a huge hurdle for early lithium battery development. Despite the promise of lithium, the dendrite problem made early lithium metal batteries too dangerous for widespread use. The risk of fire or explosion was simply too high. This meant that while the concept was revolutionary, the practical application was limited. It was a classic case of scientific breakthrough meeting real-world engineering challenges. The scientific community knew lithium was the future, but a safer solution was desperately needed. The challenge was to harness lithium's incredible energy density without the inherent risks of metallic lithium. This pushed researchers to think outside the box and find a new approach. The breakthrough came in the 1980s with the work of John B. Goodenough, Akira Yoshino, and M. Stanley Whittingham. Instead of using pure lithium metal, they developed a battery that used lithium ions. These ions could move between the electrodes without forming dangerous dendrites. Goodenough discovered a stable cathode material, lithium cobalt oxide. Yoshino then developed a carbon-based anode that could intercalate or absorb lithium ions. This meant the battery no longer relied on metallic lithium. This innovation led to the first commercial lithium-ion battery by Sony in 1991. It was a game changer, making portable electronics truly portable. Batteries, especially lithium-ion ones, can explode due to a phenomenon called thermal runaway. This happens when an internal short circuit or external damage causes the battery to overheat. Once a critical temperature is reached, the internal chemical reactions accelerate uncontrollably. This rapid increase in temperature and pressure can cause the battery casing to rupture. The highly flammable electrolyte can then ignite, leading to an explosion or fire. It's a chain reaction. often triggered by manufacturing defects, overcharging, or physical damage. While we don't recommend trying this at home, understanding the mechanics of a battery explosion is crucial. Imagine a small, contained chemical reaction suddenly going wild. When a battery is severely overcharged or short-circuited, the internal resistance drops dramatically. This causes a massive surge of current. This current generates intense heat, vaporizing the electrolyte and building immense pressure. The battery essentially becomes a tiny pressure cooker. When the pressure exceeds the casing's strength, it bursts, often with a violent release of energy and flames. It's a powerful reminder of the energy stored within these everyday devices. From simple chemical reactions to complex ion movements, batteries have evolved dramatically. They are a testament to human ingenuity, constantly pushing the boundaries of what's possible. The next time you pick up your phone, remember the incredible science packed into that small, powerful device.